Hi, today we're going to talk about transistor amplifier classes, specifically class A, B, AB, C, and D. So amplifiers are classified by their degree of operation. The classes are related to the time period that the active amplifier device is conducting current. So if we look at our graph here, what happens is that we can have an amplifier that will only conduct for 180 degrees, or could conduct for 360 degrees, or it can conduct for less than 180 degrees or a little bit more than 180 degrees. We rate it as in degrees from 0 to 360 degrees, which corresponds to 0 to pi to 2 pi, and that would be considered one full cycle. First amplifier we'll look at is a Class A. A Class A draws current throughout the circuit from 0 to 360 degrees. So we'll see a complete cycle. One complete cycle is 0 to 2 pi. It's not efficient because it is always drawing power. So an amplifier example is the voltage divider amplifier. Voltage divider biased transistor amplifier is a perfect example. It conducts from 360 degrees. So we'll have V in, we got a sine wave in, we'll get all 360 degree sine wave out. And whether or not we have a signal coming in, we will still have current being drawn through the circuit. We'll have our collector current being drawn. Class B amplifier draws current through the circuit from 0 to 180 degrees. So it'll only conduct from 0 to 180. Which is half a cycle, and we describe that as pi, so it'll conduct from 0 to pi. It's efficient because it only draws power during its half cycle, so it'll only draw power during this first 180 degrees and then will do nothing. If it's on a negative amplifier, it won't do anything on this cycle, but then it'll conduct down on this one. Class B amplifier example, it's a push-pull amp. So what we have is a transistor here and a transistor here. This is an NPN transistor. NPN transistors generally work on the positive voltage, like 12 volts. This is a PNP transistor, and usually PNP transistors work on negative voltage power supplies. Q1 amplifies from 0 to 180 degrees, a positive cycle, and Q2 amplifies from 180 to 360 degrees. The transistors are turned off for the other transistor cycles. So Q1 is turned off when Q is on. Q2 is turned off when Q1 is amplifying and conducting. So let's take a look at the positive cycle. So when Q1 turns on, we have a positive cycle coming in on its base. What happens is it pushes the current through our load resistor, our 100 ohm load resistor. One of the things you might notice is that we will have our input signal comes from our signal generator through the capacitor, through junction A, up into the base, and then it comes out the emitter. So when it comes out the emitter, that's a voltage follower. So Q1 is operating as a voltage follower. Class B amplifier, the negative cycle, the bottom transistor starts working. What we have is on our signal, we get our negative half cycle of our sine wave coming in. It then biases, it comes into the base of Q2, and then Q2 acts as an emitter follower, and then it goes out through here. But now what happens is that if we look at, we'll go back one here if I can do that. So on the positive cycle, it flows from positive 12 through the resistor to ground. On the pull cycle, it pulls from ground through our resistor to minus 12. So what we actually see is that we get our push from Q1, our positive voltage going into, and current going into a resistor, and then Q2 pulls it, and that's where we get the name push-pull. So the top transistor pushes the current through the load from 0 to 180 degrees, and the bottom transistor pulls the current from the load from 180 to 360. The change in direction of the current gives us our positive and negative voltages. So when the current's going this way from plus 12 to ground, it's a positive voltage. When we go from ground in the reverse direction to minus 12, we get our negative voltage. Class B amplifier biasing. The input signal biases the transistors on. So in order for Q1 to start conducting, the input signal must be greater than the base emitter voltage, which is 0.7 volts. In order for Q2 to conduct, the input signal must be greater than minus 0.7 volts on the base of Q2. So let's take a closer look at Class B biasing. So what we'll find is that if we look at our base resistors, R1 and R2, they're just a voltage divider. Now, because they're a voltage divider, the same current is going to flow through both of them. Both resistors will have the same voltage drop. Now, because they have the same voltage drop, and this one has plus 12 and this one has minus 12, junction A is going to be in the center. It's going to be creating a virtual ground, so it will be 0 volts. Cap C1, basically what it does is it takes a signal generator and couples our signal onto junction 1, which is our 0 volts DC. All right. So one of the things that happens is that in order to turn on the transistors, we have to make the base emitter voltage. We got to reach 0.7 volts. So I'm looking at just the positive signal coming in, the positive half cycle, and this is our input voltage. What happens is that it has to climb up to 0.7 volts in order to turn on the transistor and have that transistor start conducting. So we get a little time frame here where nothing happens. Right? So it's climbing up, nothing happens. Then the transistor starts conducting on its output. It comes down, and what we have, the input starts coming down. It hits 0.7 volts, and the transistor stops conducting. So when it stops conducting, our output goes to 0. So we have this little time frame, nothing happens, it starts conducting, it stops conducting, and nothing happens. If we combine the signals together, what we'll find on our output, we'll have our positive cycle, it comes down, stops conducting, and then it goes on the negative side. The negative side signal, it has to wait to minus 0.7, so there's a delay from it, and then it starts conducting. If we take a close look at this crossover point, what we find is that instead of having a smooth crossover from positive to negative half cycles at the 180 mark, is there's a delay. This is called crossover distortion, and it's not desirable. A solution is to use something called a Class AB amplifier. This adds a little bit of biasing to the transistors in a push-pull circuit, and the transistors actually conduct for a little bit over 180 degrees. We add two diodes, these are called biasing diode, D1 and D2, and what they'll do is put a little bit of bias on Q1 and Q2. So if we take a look at just the positive cycle of the biasing, what we'll see is that we have our virtual ground, 0 volts. It's the same story. So if I go back here, we see we have plus 12 volts, R1 a 10K, a diode. Then we have another diode and a 10K to a minus 12. A is still in the center between these two voltages and becomes a virtual ground. The base of Q1 will now be biased at 0.7 volts, which just turns on the transistor, right? It needs 0.7 volts to turn on. We've got a diode here, we've got a resistor, we've got a virtual ground, so we know it's going to be about 0.7 volts. Any positive signal coming in here is going to be superimposed on this point. So what happens, as soon as we get a positive signal here, this diode starts conducting. When we look at the negative cycle, we have our virtual ground up here. We have a diode. This point's going to be biased to negative 0.7 volts, which will just turn on this transistor. As soon as we have a negative half cycle come in, it's going to start, this transistor is already ready to conduct, it'll start conducting immediately. By providing a small bias to the transistors, crossover distortion is eliminated. There's no crossover distortion here because the transistors have already been biased slightly on. A Class C amplifier amplifies with a conduction angle of less than 180 degrees. It's used for tuned resonance circuits such as the carrier frequency for an RF transmitter. It's very efficient at one frequency. So what we'll find is that it's only going to conduct for a very short time, less than 180 degrees. So a Class C example is what we have is a tuned circuit, resonant circuit. So we have an LC resonant circuit, and it's going to ring or resonate at a certain frequency. But what will happen is it can't keep resonating, it'll start decaying. So what we do is we have an input and we put a spike in here. When the spike hits here, the transistor turns on briefly, hits this LC network, and it starts resonating. It keeps ringing and it stops the decay. It's very efficient for the tuned circuit because we just kind of have to hit this once briefly and then this will resonate. And that one of the problems is it's a distorted output signal. This is used for typically transmitters, AM transmitters, FM transmitters, RF transmitters, and it's extremely efficient. The last circuit we'll look at is called a Class D circuit, and it's a digital circuit. Typically used for, in this case, audio amplifiers. All modern audio amplifiers use it. Super efficient, lightweight. It's about 1/5 the weight of a Class AB circuit. And how it works is we take our analog input signal, our sine wave, and we convert it into a pulse width modulated signal. The width of the pulse here corresponds to the amplitude of the output signal. Right? So we convert the analog signal into a pulse width modulated signal. We run it into a output stage, which is just a switching controller and output stage. The only thing that's happening here is we're switching it on and off, and this is where the efficiency comes in because we're not in the analog region where excess energy is dissipated as heat. It's either off or on, and we have a pulse width modulated output that's can provide lots of current, and we run it through a low pass filter. A low pass filter, what it basically does is convert by the charging discharging time of a capacitor, it converts this signal into an analog signal. So it's very efficient compared to Class A and AB circuits. Most modern amplifiers are based on this because they're smaller, they're lighter, they use less components. They don't need big monster transformers in that. So if we look at an amplifier class comparison, Class A is full cycle, 360 degrees of conduction, and conduction angle is 2 pi. So theta is called the conduction angle. Class B is a half cycle, 180 degrees of conduction. Theta is equal to pi. Class AB is slightly more than 180 degrees of conduction, so we say theta is between pi and 2 pi. Class C, slightly less than 180 degrees of conduction, so theta is less than pi. Class D is on-off nonlinear switching. Theta is equal to 0. There's no conduction angle. It's either off or on. This completes the discussion on classes of amplifiers. I hope you guys have a great day.